Alright, so in this video I'm gonna be talking about another approach for sentence embedding, and we are using contrastive learning to do that. And this is an advanced version of SIMCSE. I've explained SIMCSE in a different version, in a different video, and so I'm gonna be focusing on this article in 2023. This paper improves contrastive learning for sentence embeddings from two perspectives, handling dropout noise and addressing feature corruption. Specifically for the first perspective, we identified that the dropout noise from negative pairs affects the model's performance. Therefore, we propose a simple yet effective method to deal with such type of noise. Secondly, we pinpoint the rank bottleneck of current solutions to feature corruption and propose a dimension-wise contrastive learning objective to address this issue. Both proposed methods are generic and can be applied to any contrastive learning based models for sentence embedding. This is our goal, and we use contrastive learning for that. As I said, bottle twins is just a very simple approach for contrastive learning. So why not use it for this feature corruption issue that we have? Because feature corruption is a non-trivial problem where each dimension of the model shares high similarities with others. This issue hinders the expressive capacity to convey some complex information effectively, as the diversity of each dimension value is constrained by such correlation. So we should know that even bottle twins has a rank bottleneck issue, and these are important articles that are talking about this important issue. But we can improve dropout noise in contrastive learning. SIMCSE, which I've explained in a different video in a playlist for contrastive learning, plays a central role in recent sentence embedding strategies. It is a simple contrastive learning framework that learns by identifying positive pairs among in-batch negatives. Specifically, for a given sentence x sub I, let F denote the pre-trained language model, and it is used to generate two views. So we have created two views here of identical sentences. So we give one sentence, so it gives us two views. And then we use this info NCE objective that you are very familiar with. So we can use dropout noise in negative estimation. So dropout is determined by the random variables C, and thus Z sub I contains the noise due to the random variable. So to study the effect of dropout noise, we respectively add more noise or reduce some noise, and then study their final performance. So these are Gaussian with mean 0. We are adding to that, and they have variance 0.1. And according to central limit theorem in statistics and probability theory, the K sample average converges to its expectation with 1 over K of the original variance. Therefore, to reduce the noise, we could simply use just this mean sampling. We are just using this mean sampling, taking the average. And these, you can see, are independently sampled from the dropout variable. So the solution of this paper is called off dropout sampling. So It turns off the dropout when sampling negative example representations. Off dropout sampling produces representations with zero variance. At a high level, off dropout sampling is empirically equivalent to the mean of infinite times resampling. So the InfoNC objective for off dropout sampling is now this. And S here is just the similarity between negative pairs, and Z sub I, Z sub J are the representation sampled without dropout. M here is just the trade-off between positive and negative pairs. So we have feature corruption issue, and so the existing solution for this contrastive learning, as I said, Barlow twins is very simple. I've explained it in playlist for contrastive learning. You just need to create this cross correlation matrix, and that's it. Because if you create this matrix, then some entries use it for the loss, and you backpropagate loss to tune your weights. And there is a rank bottleneck for Barlow twins, as I said. From a theoretical standpoint, if the denominator of that CCD remains constant, C can be expressed as the product of a matrix with dimension D times N and another matrix with dimensions N times D. So we can demonstrate that the rank of C is at most minimum of these N and D. And however, in the conventional setting, N is 64 and D is 768. But the solution of this paper is dimension-wise contrastive learning. Because previous experiments have confirmed the existence of rank bottleneck issue in Barlow twins objective and have addressed this problem by padding artificial embedding. However, optimizing parameters with a large number of artificial embeddings reduces training efficiency. Therefore, we propose this dimension-wise contrastive learning that naturally avoids this rank bottleneck issue that we have. So this is the objective, and the term S here calculates now the cross-dimension similarity between the C's and the D's dimension. And we use a dot product with batch normalization. So we normalize it here. This is variance and the mean. And then we can combine these, and lambda is just a hyperparameter. It's a trade-off between these two different objectives. And this is the SIMCSE plus examples from this data set, which contains 150,000 sentences. And like any other algorithm in the world of contrastive learning, contrastive networks, we can measure how successful we are by seeing which point in this space we are. So, of course, this one is our final goal in research in NLP, but it's hard to go in this region, so that because if you get good uniformity loss, then you have very bad aligned loss, and vice versa. So, and the alignment and uniformity loss, which I've explained several times,